Hello and welcome back. So now that we know what we're going to do, we're going to start by looking at estimating the first property. And so we're going to talk about parameter estimation, and we'll also have a mean example. All right. So first, if we want to talk about estimation, we need to say what estimators are. So as we know, we're taking a sample, which is a sequence x1 up to xn of independent samples from a distribution or a population, and we denote it by x superscript n, just the sequence of all n samples. And from the sequence, we want to estimate a distribution parameter theta. For example, theta could be the mean or the maximum value in the distribution or the population, and so on. Okay, so mean or standard deviation or the largest value that has positive probability, or the largest value that appears in the population. And we do it by using an estimator. An estimator for a parameter theta is just a function, theta hat, that takes our n samples and map them to some real number, which is the value of the parameter. Okay, so it just maps xn to the sequence of n values to a number which is the value of the parameter. For example, we could take the maximum. If we took n samples to get x1 up to xn, we can take the maximum value that we observed, or we can take the average. So any of those is an estimator. It just maps the observations to some value. And upon observing a sequence xn, we're going to estimate the value of the parameter by looking at this function theta hat, and applying it to xn. Okay, and we're going to call this theta hat capital theta 8, because this, you observe, is now a random variable. Okay, so this is a random variable which is a deterministic function of xn. Okay, so, and we're going to do some examples very shortly. Okay, so basically we observe xn, and then we apply this deterministic function, for example, the maximum of all of that, and we get a random estimate, which we call theta hat. So theta hat is a random variable, and it is our estimate for the value of theta, for the parameter that we want. Okay, so just a couple of observations. You can see that we're observing a single value, namely for every sequence xn we get, we just apply this function, so we get a single value, let's say 3.5, and this kind of estimated is therefore called a point estimate, as opposed to giving an interval, saying that there's a range of possibilities. Okay, and also note that any function could be an estimator. We can take the product of the values you observe, the maximum, the sum. Any of them is an estimator. Now, how well does it do when trying to estimate a specific parameter differs, so it can be either good or bad, and our job is, of course, to try to come up with good estimators for different parameters that we want to estimate. Okay, so how are we going to do it? Well, we're going to take a page from Elon Musk. He has experience in opening many companies, including, for example, Tesla or SpaceX, which launches rockets into space and often are successful. And so we're going to do the same. We're going to have sample X, which is a very simple technique that will let us come up with an estimator for any parameter that we want. And like Elon Musk's SpaceX, often it will work well. All right. So let's look at this sample X. So we're going to have a property. Let's call it property X. And based on that, we'll get sample X, which is going to be an estimator. So take, for example, the minimum. So let's say we want to find the minimum X min, which is just the smallest X that has positive probability. So for example, if the distribution is normal, then X min is minus infinity. But if the distribution is uniform from 5 to 7, then X min is 5. Okay. Then what we're going to do is we're going to apply the same thing to the sample. So we'll call it the sample mean. We're just going to look at all the values that we observe, and we'll say that our estimator is the smallest of those values. So if we observed the values 5, 3, and 9, and then the sample mean, the sample is 5, 3, and 9, and the sample mean is going to be 3. Or if we're looking at the maximum of all possible values of the distribution or the population, call it x max, is just the max over x of all elements x whose probability is positive. So, for example, if we take uniform from 7 to 9, then the highest possible value is 9. And then we're going to just have sample x, in this case called be the sample max, which is just the maximum of the values that you observed. So for example, if the distribution was from 5 to 9 and we got the values, or 7 to 9, and we got the values 7.1, 7.8 and 8.4, then the sample maximum is going to be 8.4. Or if we want to estimate the mean of the distribution, which, as we know, we denote by mu, that's just summation of x times px, then what we're going to do is we're going to do the same thing for the sample that we have. So we're going to look at the sample mean, which is just the average of all the values that we observe. Okay, so if the values we observe are, for example, 1, 3, and 5, then 1 plus 3 plus 5 is 9, and the average is 3, so the sample mean in this case is going to be 3. Okay, so what we did here is we saw that a simple way to come up with an estimator for any property. If you give us a property, we just look at the same property, but just apply it to the sample. And so this is our sample x method. Sample could be sample mean, sample max, sample average, and so on. And so we have this method, and just like space x, it often works well. All right. Okay. So now that we have described different estimators, the question is which one, are we going to use? So we have a property and can have several estimators. We described one of them, the sample x method, but you can come up with other estimators. And so we want to evaluate the quality of an estimator for a parameter. Okay, and we'll describe first two related values, bias and variance, and then another one that encompasses both of them. It's called the mean squared error. Okay, so first, what are the bias and the variance? So if theta hat is an estimator for theta, and you recall that theta is the parameter we want to estimate, for example, the mean, and theta hat is our estimate, which is based on the sample that we observe. And then the bias of theta hat is its expected overestimate of theta. For example, if the mean is 4 and the expected value of our estimator is 5, then the bias is going to be 5 minus 4, which is 1. So just written here, the bias of the estimator theta hat, which is a random variable for the parameter theta, is just the expected value of theta hat minus theta, which is the same as the expected value of theta hat, or its mean, mu theta hat, minus theta. Okay, and if the parameter we're trying to estimate is clear, for example, if we are talking like for 5 slides about the mean, then we're not going to write theta, we'll just write, which is the parameter, we'll just write the bias of the estimator that we have. Okay, and if the estimator has 0 bias, then it's called unbiased, and that would mean that that the mean of our estimator is exactly theta, right? That this difference is 0, or that the mean of the estimator is exactly theta. Okay. Now, the variance of an estimator is just, as the name says, it's just the variance of the estimator, which is the expected value of the estimator theta hat minus its mean square. Okay, and notice that this variance is defined just for the estimator. It has nothing to do with what we're trying to estimate theta. It's unrelated to theta. Okay, and ideally we would want an estimator which has 0 mean and 0 bias and 0 variance. If we have an estimator that has 0 bias, that means that its mean is just theta. And if it has 0 variance, it means that it's a constant. So that means that we have an estimator that always gives us the value of theta. It's hard to get an estimator like this. We can only get that for distributions that are constant. So typically there'll be some trade-off between the bias that we get and the variance that we get. Okay, and now. So this is all good, and the only thing is that, as we see, we have now 2 measures. One is the bias and one is the variance. And while in life 2 is good, in math 2 is not good because you have some trade-off and you don't know how to choose. So we want to define like a single estimator, okay, and a single evaluation measure for the estimator. And the one we'll use is the mean squared error, which is a single measure for the performance of an estimator theta hat for a parameter theta. and it's abbreviated MSE. And the mean square error of theta hat is just its expected square distance from theta. So the MSE, we denote like this. It's the MSE of the estimator for the parameter. Okay, it's just the expected value of the estimator minus the parameter squared. Okay. And if the parameter we're trying to estimate is clear, then we just denote it by the MSE of theta. Okay. And this is common in science and engineering. For example, when people design communication systems or transportation systems or production facilities, they often use this parameter. They want to design something and they want to minimize the mean square error. So they have some target and they want to minimize this difference square. Okay. And so one natural question is whether if we want to do this, we'll need to do something. We talked about bias and variance. Well, we need to do something which is completely new, and luckily, no, because we can relate this to the bias and the variance of the estimator. Okay, and what help us is what you might call what help us use the bias and variance is what you might call the bias variance bromance, which is that the mean square error is the bias square plus the variance. And to see that, recall that the variance of a random variable x is the expected value of x squared minus the expected value of x squared. Okay, so the variance of x is e of x squared minus e of x squared, which we can write like this. The expected value of x squared is the mean squared plus the variance. Okay, and if you want, you can think of it as maybe the probabilistic version of a physical truth. So in physics, we know that the energy is E, the energy is mc squared, and here we can think of the expected value of x squared as the energy of x, and so we have that the energy of a random variable is its mean square, is mu square plus sigma square instead of the m times c square. Okay. All right. So what we want to show is that the MSE is equal to the bias square plus the variance. And to do that, let's look at the MSE of theta. I omitted here theta hat, just wrote it as theta, is the expected value of theta minus the parameter squared. Okay, so we have, if we call theta the estimate minus the parameter, we call it x. And then we have here the expected value of x squared, and this is going to be equal to the expected value of the difference squared plus the variance of the difference from here. Okay, but the expected value of the difference is just the bias, and the variance is just the variance. Okay, the variance of what we define to be the variance of theta. And because what we do here is we subtract theta, which is a constant, and we subtract the constant, we don't change the variance. Okay, and when we combine those, we see that what we get here is just the bias squared plus the variance. Okay, so this gives us a very simple relation that relates the MSE to the bias and the variance. All right, so what is our mean example that we're going to give? Well, it's probably not so surprising, it's just the mean. So suppose we have an unknown distribution or population, call it P, and we want to estimate the mean mu. Okay, so we're going to take n samples, x1 up to xn, and they're distributed according to P, and they're independent of each other. And what we're going to use is the sample x method that we said. In this case, it's the sample mean. And what is the sample mean? We take all our samples, n samples, we add them up, normalize them by n, and we call it our mean. Okay? And what we want to do is we want to evaluate the bias, the variance, and the mean square error of this estimator. Okay? And if things will look a little familiar, if you have a sense of deja vu, there is a good reason, because we have actually done this before. So when we talked about the weak law of large numbers, we said that if you take a bunch of samples and take the average, we saw what the mean was, we saw what the standard deviation was, and that's exactly what we're going to do again here, except we're just looking at it in the context of a sample, but the calculations are going to be exactly the same. Okay, so it's the same as what we saw for the weak law of large numbers. Okay, so first let's evaluate the bias of the sample mean. So sample mean, as we said, is just the average of our n samples. Okay, And what is its expected value? Its expected value is just the expected value of this average. And by the linearity of expectation, we can take 1 over n outside of the expectation and also take the summation outside of the expectation. So it's going to be 1 over n times the summation of the expectation of xi. Now observe that each xi was chosen according to p. So the expected value of each xi is the expected value of p, which is mu. Even though we don't know what mu is, we're trying to evaluate it, but the expected value of xi is mu. And so what we have here is n times mu, right, divided by m, which is just mu. So what we get is that the expected value of the sample mean, x hat, is just a mu, which is the average of the mean of the whole distribution or the mean of the population. It's kind of nice. It says that if we take a sample, calculate the average, then its expectation is exactly the value of the parameter that we are seeking. Okay, and therefore the bias of the sample mean is just the expected value of this is the bias, is just the expected value of our estimate minus mu, what we're trying to estimate. Okay, but this is just going to be mu minus mu, which is 0. So in other words, we see that the sample mean is an unbiased estimator for the distribution mean. Okay. Next, we're going to look at the variance of the sample mean. Okay, so the variance of the sample mean is the variance of this average. Okay. And now recall that our samples are independent. Now, if we're sampling from distribution, they're really independent. If sampling from population, we assume that we're taking few samples, so they're effectively independent of each other because we don't get repetitions. And so, first of all, we know that the variance of a constant times a random variable is the constant square times the variance. So 1 over n comes out as 1 over n squared. And now we're going to use the independence and get it's 1 over n squared times the summation of the variance of the xi, because the samples we're assuming independent. And so, but the variance of each xi is a sample from the distribution, which has a standard deviation sigma or variance sigma square, which is unknown to us, but it is still the variance. So we get 1 over n times the summation of 1 up to n of sigma square. So sigma square will get multiplied by n and then divided by n square. So we get that the variance of the sample mean is sigma square over n. Okay, which is kind of nice. It says that once we take the sample mean, then the variance of our mean is going to go down with n. Okay, and the standard deviation, therefore, is going to be the square root of this, which is sigma divided by square root of n. So we see that both of them increase with the original standard deviation of the distribution of the population. They increase when sigma increases, but they decrease with n. So if we keep increasing n, then eventually these values will become smaller and smaller. Okay. So now we calculate the both the bias and the variance of the sample mean. We can therefore calculate the mean square error. But before we do that, I want to show you a couple of experiments. So these experiments you can find in the notebook for this lecture, and you can play with different values using the sliders. So here what we have is a underlying Gaussian distribution with mean 0 and standard deviation 1. Okay? And we're going to select samples from this distribution. In this case, we're selecting five samples, sample of size 5, and we're going to calculate the average. Okay, and we see what we get. And now, if we did that once, then you'll just get a single spike, but we won't see what happens on average. So we'll repeat this process in this case 3,000 times. Okay, and what you see is that you see the distribution that you get for the sample mean, and you can see that its expected value is roughly 0, what we expect to get, and you see the variance of the sample mean, which is pretty wide, and that's because we only took 5 samples. Okay. Now, if instead of taking a sample of size 5, if we take a sample of size, in this case 50, then you can see that the sample mean becomes much more narrow, and that's because its standard deviation or its variance decreases, like sigma square over n, and we get a better estimate. But still, in both cases, the expected value is essentially 0. because that's what the expected value should be. Now this was done with repeating this 3,000 times. If instead we repeated it only 400 times, then you'll see that the results are going to be a little more sketchy. It's less clear what's happening, and also now when we look at the average, while the expected value is still 0, because we're taking fewer samples, there's more statistical variability, and maybe the expected value is not exactly 0 in this case, or further from 0 than it was above. And here again, we're taking more samples, then we see that it behaves more focused, but again, maybe the mean is not as close to 0 as it is here, because we took fewer repetitions of this experiment. Okay, and finally the MSE. So the MSE of the sample mean is the bias square plus the variance, and the bias as we saw was 0, and the variance we saw was sigma square over n. So this gives us sigma square over n, and as we said before, it increases with the original standard deviation of the distribution, but decreases as the number of samples that we take increases. And a couple of nice things about this is that this estimator that we have, the sample mean, works for any distribution. We don't care what the distribution is, if it's Gaussian, if it's normal, if it's continuous, if it's discrete. The sample mean works for all distributions. That's one thing that's interesting. And the second thing is that the accuracy that we get here, namely the mean square error, it depends on the sigma or n, but does not depend on the population size. So for example, if you're looking at, if trying to estimate the average size of people in your class, or people in your school, or people in the whole country, that won't matter. The only thing that would matter for your accuracy of your estimator is just what is the standard deviation, which presumably is the same, no matter what, whether you're looking at small class or large collection of people, and n, which is the number of samples that you took. So if you took 100 samples, you can estimate the average for your class or for the whole universe equally well. Okay, all right. So with that, we talked about what parameter estimation is. We described what it means to have an estimator, how you evaluate an estimator using the bias, the variance, and the mean square error. We described a general technique for creating estimator, which is looking at the sample X, or the sample, for example, sample mean, and so on. And we evaluated this sample mean for estimating the mean mu of a distribution. Okay, so this is what we want to say about the mean, and what we want to do in next time is estimate the variance of a distribution. See you then.